this is Project Team 3, which is a very snappy name. No one gave their teams good names this year. Anyway, they're going to talk about the semi-automated cattle stock management system, and let's start when they're ready.
Okay. Australian cattle farms are experiencing attrition rates higher than ever before. Every year, up to 48% of Australian cattle lose their lives due to undetected bovine-borne diseases. This costs Australian farmers over $270 million every year. A cost that can be avoided through implementation of the appropriate technology. What if each cattle was equipped with a cattle tag that could sense the cattle's health vitals, where a drone collected this cattle tag, this cattle vital data, sent it through to a database, which then to a human-machine interface that alerted the farmer of their cattle's health and location. This is the essence of the semi-automated cattle management system that myself, Nikola, George, Rowan, Branden and Jade have fostered over the duration of this semester. The goal of this project was to assess the feasibility of a drone-based cattle management system. Now, the first individual component to be discussed is the cattle tag exterior. This encloses the circuitry. Now, as we can see on the visualizer, we have a prototype for you. Now, this cattle tag exterior will protect against intrusion and environment and provides attachment to the cattle's ears. In communication with our project sponsor, Mr. Simon Chan, through semi-structured interviews, we'd identified that this tag exterior must be able to withstand temperatures from 0 to 4 degrees Celsius, a UV rating of 14, an ingress protection rating of 40, and be suitable for radio frequency identification technology. It needs to be low weight and profile and last for 3 years, which is the average lifespan of our cattle. Now, in order to meet these requirements, it's essential to have an understanding of the relevant standards and regulations. The Biosecurity and Agricultural Management Act of 2013 states that each cattle in Australia requires a National Livestock Identification System tag. This identifies the paddock in which the cattle originated. So it was initially proposed that we integrate our system with this tag, so this tag exterior doesn't need to be designed. However, the Act disallows integration of 2 different management tags. But communication with potential clients says that it's not a problem to have 2 tags attached to a single cow. This eliminates that market entry barrier that we'd identified. Now, also, there were no standards for size, weight, shape, or material for cattle tags. However, competitive products ranged in weight and dimensions. So the heaviest tag identified was 669 grams. And the largest dimensions ranged from, well, they went up to 74 millimeters by 60 millimeters. So as long as we were within these limits, we were able to avoid imposing any harmful side effects for these cattle. So now we needed to meet the remainder of the requirements. Now, as we can see from the diagram and from the visualizer, that there are 2 parts of the tag. There's the tag body, and there is also the tag clip. The tag body includes that circuitry, and in order to mitigate the risk event of combustion of those circuitry elements within the tag body, fire-retardant ABS plastic was chosen. This withstands temperature range from -35 to 8 degrees Celsius, has a low dielectric value of 3.0, which means it will not attenuate any RFID signals, which will integrate well with the RFID transceiver, has a high impact strength, which means it can be dropped from the 1.94 meters, which is the tallest cow ever recorded without any damage, and must integrate in terms of having a volume of 2.14 centimeters cubed within. That will allow space for the sensor array and other components. Now, the tag clip is on the back of the tag, and that gets direct exposure from the sun as the cow puts its head down and feeds. So the chosen material was UV stabilized ASA, and this can withstand direct exposure to UV for 10 to 15 years. Again, low weight, low dielectric value. I'll now pass over to Nikola to discuss the sensor array.
Thank you, Thomas. So the sensor array. The sensor array is the group of sensors that reside within the cattle tag exterior to measure the cattle vitals. Now, these cattle vitals are in accordance with the requirements set out by our project sponsor, which are: the cattle tag must measure ear temperature once every 15 minutes. This would be done using a temperature sensor. The second requirement was the cattle tag must measure movement once every 15 minutes. This would be done using an accelerometer. Now, in order for the sensor array to function within the system, it would have to be able to be compatible with the cattle tag exterior and the microcontroller. So what does that mean? That means that the sensors have to be small enough to fit within the cattle tag exterior, and they have to be able to send data in a format which the microcontroller can interpret. So, choosing the temperature sensor. Well, there were three main candidates for the temperature sensor. The first was the fever tag. Now, the fever tag has shown good results in the past, but the problem with the fever tag is that it would be another tag we'd have to incorporate in conjunction with the tag that you see here. This would add extra bulk to the ear, extra weight to the ear. The second sensor that we considered was a cheap temperature sensor that we could make into a probe and put inside the ear canal of cattle. Now, after discussing with cattle farmer Mr. Ian Nikola, we found out that for a cattle tag to be more durable, there should be no loose parts and should be as less bulky as possible to make it more durable in case cattle would rub its head against a tree, try to take it off. Therefore, these two sensors, the feeder tag and the digital sensor, would be taken out of the equation. So the third sensor we looked at was an IR sensor. Now, the great thing about this, it's a single rigid body that we can put inside the cattle tag exterior. And it's shown right here. This is the temperature sensor that we chose, the IR sensor. Now moving on to the accelerometer to measure moving. Now at the time of selecting the accelerometer, we were almost over budget. So I chose an accelerometer which was cheap. I also chose one which would be able to interface with the microcontroller, and I chose one which was small enough to fit inside the cattle tag exterior. Now at the moment we measure cattle movements for 8-second bursts in 15-minute intervals. In future, we want to keep the accelerometer on for longer to get graphs like the one that you see on the bottom right. Highlighted in orange is what it looks like when the accelerometer measures feeding of cattle. And why do we want to measure this? Well, if we can sense feeding times, then we can get a good understanding of how much nutrition the cow has. And this is a great determinant on whether your cow is healthy or not. So this is a future improvement we would like to implement. But battery technology isn't quite there yet. Anyway, I'll now hand you over to George, who will talk about the cattle tag microcontroller. George?
Thank you. So the cattle tag microcontroller, remembering this is about the flow of information from cow to server. The cattle tag microcontroller facilitates this by interfacing with sensors as described by Nick, buffering that data in its internal memory, interfacing with the radio, which Rowan will discuss in a moment, and also powering all of the components within the cattle tag exterior itself. So in order to meet these functions, we also had to satisfy the client requirements. So the cattle tag had to be able to last 3 years, which is the life expectancy of these cows. It had to be able to store data for 7 days in case a cow were to wander off and not be able to be picked up. It has to be able to take measurements from these cows every 15 minutes using the sensor array. And also has to be a low weight and profile in order to make it ergonomic for the cow to wear. So in order to satisfy these functions and requirements, lots of trade-offs and compromises have to be made. And so I had to integrate with other team members on this issue. So for instance, the more data we gathered, the more energy we'd have to use to gather the data, the lower the life of the tag, the higher the range that we tried to achieve with the transceiver, the more current the tag drew, and hence the lower the life expectancy. And also there were base constraints regarding the cost and the size of the tag. The cost was driven by, of course, by budgetary concerns, and the size in order to fit within the small casing as shown in the visualizer of the cattle tag exterior. So after all of that was juggled around, the final design decisions were made, and so data storage, a microcontroller, and a battery were used to satisfy the functions required. So the data storage was chosen to be a micro SD card, and it was chosen for its high information density, its small size, low cost, ready availability, and very, very low idle current consumption. Unfortunately, the low write speed of the micro SD card is a drawback, but as we can see, the microcontroller makes up for this with its high-speed RAM memory, even though it's much smaller. So the microcontroller chosen, the Amiga 328P, has easy integration, small size, low cost again, and again, very low current consumption for its class, but unfortunately, only a small amount of onboard storage. The batteries chosen were two CR2032 coin cells with high energy density for their size, small size, low cost, and again, very availability, just regular coin cells, with a low carrying capacity. This is made up for by the fact that the cattle tag exterior is being operated at a very, very low duty cycle and will draw an average of around 50 microwatts. So we can see here on the visualizer, just a rough representation of the placement of different parts and showing that they all fit inside a container. So now I'd like to pass on to Rowan to talk about the transceiver.
Thanks, George. RFID, or radio frequency identification, will be the means of communication between the tag on the cow's ear and the drone. Now, there are a range of RFID options available, such as low frequency, high frequency, and ultra high frequency, and selecting the correct type of RFID for us enabled us to take the project from a concept to a feasible cattle management solution. One such type of RFID available was the emerging UWB, or ultra-wideband. Now, ultra-wideband transmits data over a wide range of frequencies. This allows for a high rate of data transfer and also improves the signal integrity by eliminating the effect of noise and interference from the environment. I'll now discuss the design decisions and the process that we went through. While it was linear, it was not necessarily straightforward. As you can see, the first decision we had to make was whether to pursue an active or passive tag. Now, a passive tag is smaller and cheaper, however, it's only activated by the incoming radiation of the reader. This didn't satisfy the requirements that we needed in terms of range and data transmission, so we had to use an active tag. This then presented the question of whether to use traditional UHF or ultra-wideband. Now, we needed a tag that was able to transmit data at a large range, as well as operate, consuming so little battery to survive for 3 years, and only UWB was able to achieve this. This then led us to the selection of a module. We considered a range of commercially available models, and eventually decided upon the Decawave DWM1000, as it satisfied a range of criteria, particularly integration and cost. I'd like to draw your attention to arguably the 3 most significant features of the Decawave module. Firstly, you can see the read range. So it has a read range of 200 meters, which takes a lot of stress off the drone's battery. Now, we identified early that the drone's battery was a limiting factor of the project, and so to increase the read range, reduce the flight time of the drone, and therefore reduce the strain on the battery. Secondly, we have the resolution that these tags can identify. So we can identify a cow with up to 10 centimeters of resolution, which allows us to identify a unique cow within a paddock, which was a criteria that we had to fulfill for the project. Finally, there's the size. Now, the chip is quite small and compact, which allowed for easy integration within the tag itself. This was a must as we were trying to reduce the size and weight of the tag. I'll now pass you over to Branden to talk about the drone.
Thanks, Ron. The purpose of the drone system is to serve as a platform for the RFID reader. Once every 24 hours, the drone will fly the RFID reader over the paddock. The RFID reader will detect the cattle tags in the paddock, extract the data from them, and then the GPS module contained within the drone systems will geotag this data, and the drone systems will store this information for later transfer to the database. In order to achieve this, the drone needs sufficient payload capacity to be able to carry the RFID reader and the drone system. The drone also requires sufficient endurance to be capable of flying the required flight path to ensure that the RFID reader has adequate coverage of the paddock. The drone must also be easy to use. We don't expect farmers to have experience using drones or drone systems. The most significant standards relevant to the drones and the drone systems came from the Civil Aviation Safety Authority. Specifically, the drone cannot be flown at an altitude that is greater than 122 metres, and it cannot fly within 30 metres of any person that is not directly involved in the operation of the drone. That is, any person who is not the pilot. Additionally, that pilot must maintain visual line of sight with the drone at all times. When integrating the drone and the drone system into the rest of the project, as it's sort of already been alluded to, the RFID reader is the most significant integration consideration. If you have an RFID reader with a high range, then you only need a drone with a low endurance to cover the same area. Or if you have a drone with a high endurance, then a low read-range RFID reader is suitable. The relationship between these two was an important design consideration and optimised on the basis of the cost of the two components. Another significant integration consideration between these two devices was the altitude at which the drone would be flown. The higher the altitude of the drone, the greater detriment it has on the RFID read range at ground. However, the drone also needs to be able to fly over the top of things like trees and buildings and things like that it might come across. In the end, it was decided that 50 metres provided sufficient climbing range for the drone to get over trees and whatnot, whilst also ensuring that it was not too great a detriment to the RFID reader.
There were a number of design decisions that were chosen as part of the drone airborne system, and these are the components that result. The DJI Matrix 100 was chosen as the drone, as it has sufficient endurance to be able to fly over a 5 square kilometre paddock if required, which is in excess of the requirements which were outlined at the start of the project. The GPS module that was chosen was a U-Blox Neo 6M. This was chosen because it has a wide range of antenna options available, which means if the system was to be used in an area with poor GPS reception, an ideal antenna could be chosen for the project. The data transfer and storage methods that were chosen was the use of a micro SD card in conjunction with Bluetooth. Bluetooth was chosen because it is a ubiquitous standard and does not require a physical connection for data transport, while a micro SD card was chosen because it is expandable and also because it offers redundancy. If the data transmission system fails or something like that, then the micro SD card can be removed from the drone and the data can be physically transferred to the database, which I'll now hand over to Jade to talk about.
Thank you, Branden. Let's talk about data. So, a key requirement from the project sponsor was consideration at a very high level of the database and the output of the database, the data itself in the form of a CSV file. So the 4 key areas of the database I want to talk to you about. First of all is the database type. Now the database type is one of 2 options, relational or non-relational. Relational was chosen as much better because it's much easier to do initially, especially for a prototype. There's less overheads, it's much easier to set up. Tying into that is the database management software. Many options were compared and MySQL was chosen because it is free, first of all, really great for the budget, but it also has the data analytics we require. We have to remember that all the other systems we've talked about up until this point are about collecting, generating data to ultimately be stored here in the database for the purpose of cattle stock management, which in turn means data analytics. Looking at this data, figuring out which cows are sick, where they are, looking for those warning signs. That's what it's all about. And MySQL can do that. On top of that, as Branden mentioned, it also has opportunity for a graphical user interface, which means the farmers don't have to be proficient in programming, and they shouldn't have to be. Just have a nice GUI. Next is the database architecture. Basically, there's no choice. It has to be enterprise. All the other choices are smaller. They're not going to be good enough for the kind of customers you're looking at. They are big plots of land, many computers, many users. Tying into this is also the hardware layout as distributed. You can put different parts of the servers, the memory, different parts over a farm. What you don't see there is this also needs to incorporate mobile access via the internet through phones and tablets. This is increasingly important with the increasing prevalence of the Internet of Things, not only society but in industry as well. So lastly, the data. Key data comes straight from the requirements as we discussed, like temperature and movement. But thinking about that idea of cattle stock management, you also need to look at the idea of the tag and the drone. When considering integration as a whole system, we also should think about system health monitoring. Simply by monitoring the battery, you can now have predictive maintenance strategies, which means we are replacing the battery rather than waiting for the drone to run out of power, fall out of the sky, and crash. Now, a lot of work was done to work out the optimum data, such as integer or character types for each of these, and in total, it's only 1 megabyte per cow per year. And scaling that up to all the cows in the entire world, 1.5 billion cows, it's only 1,500 terabytes. Easily done under a $1,000 budget for storage. That concludes my section. In conclusion, I want to do a big thank you to Mr. Simon Chan, the project sponsor, for the opportunity for this project. And really, for all the work we've done, we've determined that yes, this is feasible, it can be done. As technology moves forwards, it becomes even more and more feasible as new technologies emerge, such as ultra-wideband. It's not a question of if, it's a question of when. And we in Australia need to be ready and not be left behind by the rest of the world. Now this project has also been the culmination of 5 years hard work, as Sally mentioned. I want to share key lessons learned with everyone here today. And it's this: just ask, don't assume. As engineers, so often we make interpretations of what we think the requirements of what things should be are. That might not necessarily be what the project sponsor thinks, or your client thinks, or what the market thinks. And the easiest way to clarify that is just ask. Throw them a phone call, send them an email, it's as simple as that. Okay, thank you very much for listening. Now move on to Q&A. Thank you.